Now we will move to Heba from NYU. She will be speaking about Memristor-based PUFs for cryptographic randomness. Heba, please go ahead.
Hello, everyone. My name is Hebatallah Ibrahim, and I'll be talking today on the Memristor-based PUFs for cryptographic randomness. I'm working with Professor Hebatallah Ibrahim in the Cryptography Research Lab in the Cybersecurity Center NYU AD. And this work is in collaboration with Khalifa University, Dr. Muhammad Bakr, and Heba Abu Nahla. First, I'll talk about the motivation behind our work, what is the importance of the cryptographic randomness, and a brief introduction on the PUF and what's a memristor. To ensure the reliability of a cryptographic systems, we need to focus on the power consumption area, bit generation speed, and the quality of the cryptographic randomness. True randomness can be extracted from physical phenomena such as the intrinsic variations in a CMOS circuit due to the fabrication process that cannot be exact on every CMOS circuit, and the intrinsic quantum complexity in memristors and silicon cavity. Here is a brief comparison between the pseudo-random and true randomness. Pseudo-random number generator are usually derived from a mathematical formula that would have a pattern that can be tampered with and not truly random. However, the true random number generators extract randomness from physical phenomena that cannot be predicted and have a chaotic behavior that allows it to be non-deterministic. So the true random number generators have higher efficiency normally than the pseudo-random number generators in terms of security. Moving on to the physical unclonable functions. Physical unclonable functions are advanced primitives, cryptographic primitives that are employed to generate essential true intrinsic randomness. As you can see from this figure, for different PUFs or identical PUFs but, of the same design, each challenge gives a different response. Or for the same challenge, it gives a different response. Although all the PUFs are identical, however, the fabrication process does not allow the PUF to give a same response for the same challenge. For the PUF to be successful, we needed to be unique in its output, thus have a high randomness. Reliable meaning that for each challenge, the PUF must give the exact response. And robust in terms of not being affected by the external environmental conditions, and of course, low cost. Moving on to the PUFs in literature, most of the PUFs in literature are CMOS fabricated that relies on intrinsic variation that causes the randomness. However, most of the PUFs in literature have proven to be vulnerable to attacks and can be cloned by non-invasive or fully invasive attacks. Thus, we moved to the nanotechnology-based PUF, allowing us to have a smaller footprint, lower energy consumptions, and multi-level bit capability per memory cell. Initial investigation of the nano-electronic-based PUFs are motivated by the desire to achieve more secure, robust, and lightweight PUF designs. Thus, we moved for to work with a memristor. To work with a nanotechnology, we decided to work with a memristor. First, to explain what's a memristor. Memristor is simply a device of 2 electrodes with an insulating or switching device layer in between. Here from this figure, you can see the ideal electrical switching behavior of the memristor. This is the set voltage value, and for the set cycle, and this is the reset voltage value for the reset cycle. Here you can see this is the switching layer we saw before, the red layer. Okay, to explain further how the memristor works, this is a switching layer. When we apply a positive voltage, the concentration gradient of the positive ions moves, allowing the resistance to decrease, and so thus allowing conductance corresponding to the set cycle. When we apply negative voltage between the bottom and top electrodes, the memristor switches from the low resistance side to the high resistance state with a negative potential between the bottom and top electrode corresponding to the reset. As you can see, from the high resistance state to the low resistance state set, and from the low resistance state to the high resistance state, it's a reset. And for each cycle, the resistance is different than the resistance before. This characteristic in a memristor is called cycle to cycle, meaning the resistance of each cycle is different than the previous cycle and cannot be determined by the previous cycle. Thus, it's totally random. So the inherent randomness of the memristors are due to two levels: the fabrication process and the cycle to cycle characteristics of the memristor. This is general electric properties of the memristor. However, the figures are from our memristor itself. You can see here, and this is a set and reset cycle for one memristor. As you can see, the memristor starts conducting at the set voltage, and then falls back to normal, and then the reset voltage also. It's here. This is the reset cycle, and this is the reset voltage. This figure, on the other hand, it's for different cycles of the same memristor. You can see for each cycle, the reset voltage, the set voltage is different for each cycle, and none of them are identical. And the same for the reset cycles. The reset voltages are different, and none of them are identical, and they are completely random and not and cannot be predicted by the previous cycle. Well, the memristors in general has some challenges. The fabrication process is expensive, and not all of them are industry compatible for other devices, like CMOS compatible. And most importantly, most of the studies in literature did not have or did not carry enough tests to ensure the output randomness. So our memristor is different because we built it at a low cost, and it had high endurance of over 100 cycles, passed combination of tests, including the NIST statistical tests, and it's CMOS compatible, so we can integrate it easily to other systems, and has a low power consumption. This is our proposed memristor. The proposed memristor is prepared by mixing hafnium isopropoxide, isopropanol, with sulfuric acid deionized water. And the ready hafnium propoxide solution is heavily doped with positive silicon substrate. And after the heat treatment, copper top electrodes are deposited. The cost estimated for the used materials is about $0.004. And we tested this memristor on a Kately parameter analysis that was used in the characterization of the IV properties of the fabricated device. And they were electrically tested using sweep cycling mode of step of 0.05 volt. Here again, we can see the electric properties of the memristor. This is the electric properties of our memristor. And it's important to note that depending on the material composition and the followed fabrication process, the filamentary-based switching mechanism can be highly probabilistic and uncontrolled. For this figure, this figure shows the set cycle for identical Memristor devices, thus made of the same designs, but there are different Memristors of the same design, so thus identical. However, and having the same voltage sweep. However, each Memristor is giving us a different set voltage, thus proving the randomness in the set and reset voltages of the Memristor, even having the same design. It's clearly shown that we can extract unique keys by tracing the current points on each curve, which is crucial in realizing secure PUF-based cryptographic randomness. To ensure the randomness of our Memristor-based PUF, we first evaluated the uniformity, diffuseness, and uniqueness of our Memristor. In order to evaluate the uniformity and diffuseness, we randomly applied 100 different challenge sets to one PUF. Each challenge set has 128 bits subsequently, and the 128 signal response bits are created to form a 100 multiple bit response. Each 128-bit response vectors act as an identifier of a given PUF instant. The uniformity definition, it captures the proportion of the 1 and 0 response, the ones and zeros in a response of a PUF. Ideally, the proportion should be 50% for a truly random response. The distribution of the 1 and zeros among the 100 response vectors is calculated, representing the uniformity. And as it can be shown here in the figure, the 0 percentage is 48.9, which is around 50, and the 1 percentage, it's 51.1. So the uniformity probability is near to the ideal value of 50, so it's passed this uniformity test. And for the diffuseness, diffuseness measures the difference between the response vectors for different challenges applied to the same PUF. And it's calculated by the mean of Hamming distance for all possible response vectors generated by the PUF. It's ideally 50%. And after calculating the Hamming distance between the responses of the identifiers to determine the diffuseness, it was calculated to be 49.4, which is close to the ideal value, and it's following the normal distribution. Thus, we pass the diffuseness as well. And for the uniqueness, uniqueness is measured by the Hamming distance. Ideally, the Hamming distance between the responses to the same challenge from different PUF instance should be 50%. And we use 100 different Memristor PUF instance to evaluate the uniqueness, and the result is shown in this figure. The Hamming distance, it's around the 63.3 bits out of the 128-bit response, which is almost 50%, agreeing with the ideal value of the 64 bits. We use a different combination of randomness testing, but in this slide, we'll be showing the NIST statistical test results. For the NIST statistical test results, it's 15 tests, and the p-value should be higher than 0.001 to prove randomness. Here you can see for most of the tests, we achieved a value of higher point than a p-value higher than 0.001. Some of the tests have to be shown in appendix because the results are long, but we passed it as well. To confirm the efficiency of our Memristor-based PUF, we compared it to a recent paper proposing a true random number generator Memristor. And this one of the unique papers that added some of the NIST test results that they performed. And I did a comparison between our results and their results. Our results passed or was of higher p-values, thus higher randomness than their results. Some of the results they did not provide because it should be added in appendix as well. Thus our p-values were higher than this paper's values, proving more randomness. So that was a good sign. We integrated our Memristor-based PUF to other applications like block ciphers to ensure the efficiency of our Memristor-based PUF. And also we tested the output with nested statistical tests and other tests proving its efficiency. We also integrated it in advanced metering infrastructure, where the PUFs are integrated to the head-end system and the smart meters in advanced metering infrastructure. And well, our PUF were verified to be successful in such protocols. And also we tested the output using statistical tests and other tests, and it showed true randomness or high quality of randomness. So basically our contribution with this work is providing a low-cost, high-endurance Memristor. It can be tested using non-complex circuits as most of the previous studies. But passed the combination of randomness tests, including the NIST randomness test, as we showed in the presentation. And we were able to integrate our PUF to block ciphers and AMI system and verified its reliability and randomness. Well, thank you. That's all for today. If any questions?
Thank you, Hiba. We have 15 minutes, so we can take questions for anyone who has questions from the audience. Hiba, there's a question from Alvaro. You mentioned that the cost is quite low and there are a few cycles. How close are we to seeing this applied in the UAE?
Well, the Memristor itself, it's fabricated in the UAE. So it's it's fabricated in a lab in the UAE. So it is in the UAE already.
Okay, thank you, Hiba. The second question is from Sebastian. How about the endurance? On slide 10, it was mentioned that the Memristor lasts at least 100 cycles.
Yes. Yes, it at least 100 cycles, correct.
Okay. A question from Dr. Huda is, are you considering other PUFs?
Yes, I'm considering silicon cavity PUFs, meaning photonic PUFs. It's the silicon cavities have a very high chaotic behavior. So we are trying to exploit this chaotic behavior in obtaining or also creating a true random number generator using silicon cavities. Right now, we are currently working on this. The simulation phase is done, and we are working on we'll start to work on the hardware base.
Okay, thank you. Thank you, Hiba. I guess there are no more questions. Thank you very much. We give you a virtual round of applause.